All right, today we're going to do chapter 4.6, which is a very interesting application of derivatives, and it's referred to as Newton's method, and it's a great way for discovering roots of polynomials or just other functions and trying to get really good estimates. So what Newton's method does is it takes the idea of a tangent line and then kind of recontextualizes it to say, how can I find where this value equals 0? So it's kind of pulling in that linearization idea, but it's putting it into this more applicable this applicable context. So first thing you need is a differentiable function. Without that, you're kind of out of luck. So it's a good tool, but it's a good tool for differentiable functions. Then you pick a guess. Where do you want to start? And then you solve for the root of the tangent line and use that next estimate as your next root. So this is a recursive formula in that the next term is generated from the previous. And this is our equation for it. The next term is equal to the previous term minus the function evaluated at the previous term divided by the derivative evaluated at the previous term. And then very obviously, this doesn't work if the derivative equals 0. Now, another reason it doesn't work if the derivative equals 0, if you have this function, here's where the derivative equals 0. If I draw a tangent line, this equation goes off forever. This is never going to touch the x-axis, so that's why we have to that's why we can't have a derivative be 0. And if you're wondering, well, how do you get this formula? So remember, it comes from the linearization or the equation of the tangent line. So we have y equals f prime of xn times x minus xn plus f of xn. So that's your equation. Now remember, I'm looking for solve for the root of the tangent line, which means I need to know where does the tangent line equal to 0. So we take our tangent line equation, we set it equal to 0. Okay, still doesn't look quite like the formula. All right, I'm going to divide by f prime because we're going to assume f prime of xn does not equal 0. So under that assumption, we should be able to divide. But that leaves me with x minus xn plus f of xn over f prime of xn. Now you can kind of see where it comes from. Then if I were to add xn to the left side and subtract this term to the left side, but I'm going to swap them, so I'm going to get x equals positive xn minus f of xn divided by f prime of xn. So, because what it's saying is we've recontextualized this problem now as the root of this equation is saying what value do I plug in here such that it equals this equation evaluated at the previous value. Now, if a function has a rational root, you may actually get to it and you may get those two equal. But a lot of what Newton's method is getting good estimations for, say, things that don't have a not, or that are only non-repeating decimals. So let's say, for example, I want to try and find what's the square root of 2. Well, if you punch it into the calculator, you get it's like 1.41 and some change. And there's a way to calculate that, but what if you want to use the calculus tools that you have available? Reframe the question. I'm wanting to know what the square root of 2 is, so I'm going to start with x equals the square root of 2, which is also x squared equals 2. Or I can now reframe this as I'm looking for the root of x squared minus 2. So now you don't have to think about it as, okay, well, all right, how do I go in between, like, I know it's between 1 and 2 because it's between the square root of 1 and the square root of 4. But now you have this idea, which will kind of provide you with some better idea, or not some better ideas, but it'll provide you with a different way to approach it. So then find the derivative. So f prime of x is clearly 2x if we're taking the derivative of x squared. And then we say these are the iterates because you're iterating the function over and over again for the previous problem. So the next term is equal to the previous minus x sub n squared minus 2 divided by 2xn. And then with a little bit of arithmetic and algebra, you can get this nicer single expression. So clearly we don't want the derivative to be equal to 0, which if you think of x squared minus 2, it's a parabola that goes through. Here's negative 2. And it goes through negative square root of 2 and positive square root of 2. So it makes sense that you wouldn't want to use 0 because that's one of those tangent lines where the derivative equals 0. So you're not going to be able to find it there. Now, this is the part where you want to be careful. Where you make your initial guess on some functions won't matter too much because it's going to eventually work its way to your root that you're after. Some functions where you make your initial guess are going to be extremely either helpful or detrimental to the actual function itself. So if we make our guess that, let's say x naught is equal to 1, then that means I'm going to have, if I plug it into my function, I'll get 1 squared plus 2 divided by 2, which is 3/2, or 1.5. You know, square root of 2 is about like 1.4 and some change. So now let's try this. So 1.5 squared plus 2 divided by 2 times 1.5, which is this is equal to 17 over 2, or 17 over 12, sorry, which is approximately 1.416, so on. So we're getting close. And then I'm going to do this one more time. So 17 over 12 squared plus 2 divided by 2 times 17 over 12. Got it right that time. So 17 over 12 squared plus 2 divided by 2 times 17 over 12. That's 577 over 408, which is approximately 1.41421 5, so on and so forth. And as you can see, we did our first guess of x naught was 1. Go to the function, which is f of x, which is x squared minus 1, or x squared minus 2. Draw the tangent line. That sent us to 1.5. Then go to 1.5 on the function, draw that tangent line. That sent us to the 1.416. And as you can see, it's going to get just extremely close. And so we're getting a really good estimation from, honestly, just 3 iterations. Now, again, in this case, we knew, or you kind of know, all right, if I do square root of 2, it's roughly 1.4 and some change. So if you wanted to, you could almost bypass it and just make an initial guess of 1.4, and then you're going to have really good results as you go. So, and one thing that can do this, you don't need any like extremely heavy lifting math software. You can do this with an Excel sheet. That's all this is done with. And you can just basically set it up as long as you know what your functions are. You can just set up the cells to solve this pretty easily. So with all of our initial values in place, and one other thing is, if you were to use Excel, you can either turn this whole thing, the x sub n squared plus 2 over 2xn, that can be a whole cell in itself, or you can still have an f of x cell and an f prime of x cell and an x sub n cell, which is the way this one's set up. And you can see the way that you start to see the error is to compare the term you just got from what you got it from. So this is x naught and this is x1. So the absolute difference between them is 0.5. Then I use 1.5, I get the 1.416 repeating, blah, 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 which is off by a point, which has an absolute error of 0.083. And this is what you're looking for. You want these zeros to start appearing here, because that means you're correct to that decimal place. And then here, 0.0024598. Now we're good to these 2 decimal places. As you can see, it gets extremely good to the point where the amount of error I had allowed, or the amount of decimal places I had allowed to show, gets treated as 0. Not that it actually is 0. You didn't find the exact square root of 2. It's within the tolerance you allowed. It has it's 0. Now let's say if you'd started with 2. Now if you start with 2, oddly enough, you still get to 1.5. So that one kind of works out very interestingly, because notice f of 1 and f prime of 1 are not the same as f of 2 and f prime of 2. So this one is very interesting, that going to the left or the right one, you still get the same value. Let's check 4 though. So 4 is a little bit farther away. And notice with these, the first 2, we were at, our error was 0.5. So that meant we had all of the whole number part correct. And now we were working on getting decimal places accurate. This one, we're still at our absolute error being 1.75. So we don't even have all of the integer value correct. We haven't even got to the decimal yet. So this one, you notice, starts to throw it closer and closer. And eventually you do get back to the point where you're getting really good estimates. And of course, if you do say, well, what if I try a place where it equals 0? Congratulations, you get a whole bunch of divide by 0 errors, and Excel probably hates you for it. So always avoid places where you're going to divide by 0, because otherwise you don't get any usable values, and Excel spits out this ugly looking spreadsheet. So not worth it. Now, one other thing it can do is tell you where do functions cross. So where in the function is the place where cosine of x equals x? Or where does y equals cosine of x cross y equals x? And I kind of just said it. You rephrase the question. I don't really need where does... If I'm looking for where do they cross, I'm saying where does cosine of x equal x? That means I'm looking for the root of this equation. So you recontextualize problems into, I'm looking for a root, or I'm trying to estimate this value. I'm looking where these two functions cross. It becomes, I'm looking for the root of a differentiable function. And so then what you can do, like we've done before, is use Newton's method once again. So y is cosine of x minus x. Y prime is going to equal negative sine of x minus 1. So that means x of n plus 1, if I can write it correctly, is going to be equal to x of n minus the function divided by the derivative, so cosine of x minus x divided by negative sine of x minus 1. And if you want to bring in the negative to clean it up, you can. And I need to make all of these with their subscripts. And then you would iterate this over and over again, and then this would give you a good idea of where the two functions are equal by reframing it into what is the root of this equation. So a lot of Newton's method is just reframe the idea. And you can see, as you would continue on, so 1.57, just thinking of some close values. So, and again, don't pick places where the derivative is 0. So 1.57, that's the pi over 2. Or that's pi over 2 because the derivative is negative 2, which means you did negative sine of pi over 2 minus 1. And then this continues on and on. And, sorry. When dealing with trig functions, don't use degrees, because 90 minus the cosine of 90 minus 90 over negative sine of 90 minus 1, those 90s are not going to work properly because you're dealing with 90 degrees. You need to be dealing with radians, so make sure you pick like pi over 2 and stuff like that, because otherwise, well, even just taking into account with it graphed, you can see that if you start using x sub n is 90, even though you mean 90 degrees, the problem is you need to be doing pi over 2 because that's the numeric value that's going to be closer. So just make sure you don't make a small mistake like that. So one question is, though, if you're going to make an initial guess, what are bad guesses to make? So I talked about some of them you're going to be in good shape because the way the function is going to work, nothing much is going to happen if you pick just a little bit away or above or below. The one thing you would have to worry about, like when we did x squared minus 2, is to make sure your function doesn't run off after a different root. So that's one thing you have to be careful of, is Newton's method will not always go after the root that you're after. So you do have to be careful when you pick those. So like square root of 2, or that one could have gone after positive or negative square root of 2, which would have worked out because we only needed where the sign was. But if you have something that maybe has roots that are a little bit weirder, like maybe one of the roots is cube root of 5 and then the other one is the square root of 17, depending on which one you're trying to estimate, it might go after one or the other. So you have to be aware of that. So let's say you start at x equals -1. Because sometimes you may not have it graphed, so you just have to take a look. So here's -1, and then we look at the tangent line. And this is kind of just a follow where it goes. So x naught equals -1. The next term is almost -9. So that kind of runs away really fast. Then we go down here. But now we're kind of getting into, it's starting to look okay, because now we're at roughly 3. Come down here. Next term, we're a little bit close to -1/2. Go to here at roughly 2. Not exactly, but maybe like 1.9 and some change. Come down to here, and then you're almost at that root. So starting at -1, not too bad. You get really close. You start at 4, follow the bouncing ball. You go down here, go over here, go up to here. And then, fortunately, once it hits about here, close to -10, then it kind of starts to hone back in, but it's still not quite there. So that one was a bad choice. It would still get you there, and some of them, that's the thing. They'll get you there. It just may be, you might have to let it run for a second. You start at pi over 2, though. Pi over 2, almost instantaneously there. So why is that the case? You want to avoid your small slopes, because if you notice, the more negative the slope is, the steeper it's going to send that tangent line. And this has a lot of change, because you can think about the cosine of x minus x function. What it's doing is x is still just running free. It's always decreasing. But cosine's just either adding 1 or taking away 1, or some value in between, I should say. So what ends up happening is you don't necessarily end up with a consistent derivative. So notice here at -1, the slope's kind of steep, but it's not too bad. It gets us there eventually. The problem with x naught equaling 4, that's almost where, to go back to this one, so here's 4, the slope's almost 0 here. And so if the slope is almost 0, it was kind of like one of the applications where, or there's an application in the related rates section where after like half a second, the shadow is moving extremely fast. And the reason for that is, at first the ball starts parallel to the light, which means it's also parallel to the ground, which means that the shadow's not being made like that. So if it only falls for half a second, you're talking about something that goes from infinite to touching and then is just zooming backwards. So -1 was wasn't too bad, or was a little bad, but not the worst, because notice here's another one of those points where the slope is almost 0. At -4, or at +4, sorry, the slope is very close to 0. But then at pi/2, the slope is not really close to 0. This has a kind of steady decline, so that's what I mean by small slopes. Don't pick stuff that's close to 0. That includes in the plus or minus direction. I don't mean small as in take like -1 billion. I mean small as in close to 0. So again, if you want to know where does x cubed minus x equal 1, or intersect with the line y equals 1, you rephrase the question. And then you take the function that you're trying to find the root for, and you make that your formula for Newton's, or your function for Newton's method. So our derivative is 3x squared minus 1. So our iterates are this, and again, you can always get a common denominator to make this easier. Part of the reason I would recommend getting a common denominator is you avoid compounding error if you do so. Well, you avoid more compounding error. Because remember, you're going to be going off an estimate. And if your estimate's good to 10 digits, then every time you include it, you're bringing that 10 digits of accuracy with you. And the more places you calculate it, the more places you're letting that round off error build and build. So with this one, it would build 1, 2, 3, 4 times. Versus here, it's going to build 1 time here, and then you're going to have to multiply it by 2. Add 1. That's already an integer, so not the worst thing in the world. 3 times x sub n squared. So it compounds there again. And then again, subtract the 1. But you're bringing it in only this cube term. Now, cubing with error is not really the most ideal thing either, but we've eliminated 2 other places where it can come into play. So what would your initial guess be? So as you can tell from this sheet, I think 1 is a pretty good guess, just because 1's kind of safe. X cubed minus x minus 1. If I plug in 1, I'm just going to get 1 minus 1. Or, yeah, 1 minus 1 minus 1. Which is just -1. And if I check f prime of 1, I'm going to get 2. So 2 is close to 0, but when I say small, I mean talking like fractions of between 0 and 1, typically really close. 2 is an okay choice. Could I pick something better? Probably, but usually you want to start, I typically tend to start with integers or easy decimals. Don't try and go after weird rational numbers like 22/7 or things like that. Do like a 1.25, a 1.5, a 1.3, something solid and easy to work with. And then so if you pick 1, again, here's the function's value of 2. And again, I didn't have the graph, so I'm just going to go for something that I think is close. And I also don't want to have to cube 1.3, so that's part of the reason I picked that one as well. You can see start at 1, goes down to here, throws it over to 1.5, goes up to here, down to roughly 1.3, and then it's just going to keep getting closer and closer and closer. And again, your digits accuracy is going to depend on how many zeros you have here. So, and we're talking decimal places of accuracy, because typically with these, you don't care about, well, not that you don't care. If there's an integer part of it, you're going to get that. I won't say super quick, but eventually that's what you're going to be after. And you don't really need that part with your error. That was a bad way to phrase it. You're not concerned as much with the integer part. Like I said, I know that with the previous one, like square root of 2, I know it's between 1 and 2, so I know it's 1 point something. The problem is I need that point something, so your digits accurate are going to depend on how many zeros you have. I should say this, how many sequential zeros you have after the decimal point. So like here, I have 0 digits of accuracy. Here, I've got 1. Here, I've got 3, and so on and so forth. Now, what difference does your initial guess make? I've kind of been talking about this and alluding to it. So, these are just two values, negative 1 over the square root of 3 and 1 over the square root of 3. Let's try and pick between negative 0.5 and 0.5. Well, you notice if you pick 0, this looks like it's starting to trail away, and it's getting away from you fast. Now, I said most of the time it's going to find its way back, but sometimes you may just send it off on a wild goose chase to the start. So what if we pick negative 1? Here's negative 1. It's on the other side of this hill. So it's going to go there, but then it's going to throw the thing all the way over here to negative 3, and then this function is going all the way down. And then it's because it's trying to find where your original function is. And with this cubic, I mean, over here at negative 2, it's already starting to take off. So negative 3, you're at negative 27 plus 3 minus 1. So yeah, it's starting to get away. You pick x is greater than 2. You notice kind of we did pick x was, if we had picked x was greater than 2 or about 2, we might would have run into the same issue. It might not have been as bad though, because, well, if we plug in 2 for here, so f prime of 2, that's 11, so we're avoiding that small slope, which is pretty good. But what's the key way to avoid it? The way to avoid it is to avoid a large second derivative. Because if you're trying to avoid small slopes, you're also trying to avoid large second derivatives, because remember, the second derivative talks about your concavity. So if the second derivative is large, that also means that the concavity is changing either up or down rather drastically as well. So that's one that you tend to, or that's one that I say to tend to avoid. Now, the worst case scenario, and I mean this is in the literal worst case scenario, if it's running off and it's not finding a root fast, it may just not be finding a root fast. One of the worst possible things is you could pick a point where it's just not going to find a root fast. Or you pick this case where it's just not going to find a root. Because some functions have a very weird and special case to where they just cycle. and x naught leads to x1. X1 leads back to x naught, so x naught is really x2, and then x1 becomes x3 as well. So then what's happening is you're constantly getting these points and they're never going. So you have to be very careful about points that you pick. So if you notice, it just kind of starts to, the function's already recursively defined, but if it starts to recursively define itself into an infinite loop, just call it quits and pick a new point. And I'm trying to think off the top of my head if I know any functions where Newton's method does not find the root. This is one where, given that point, it's not going to find it. Now, there may be other cases, because clearly it has a root. It's crossing the x-axis. I don't remember for this one in particular. I apologize for this. I don't remember if this function is specifically designed to where it always loops like this, because it has this very specific symmetry about it, or if this is just one key example. And one other thing is, just because you're converging on a root does not mean you're going to get the root that you're after. Functions with multiple roots you have to be careful of. And you tend to want to start closer to them. I say tend to because asterisk for almost all of these. There's always going to be something that's going to mess with this idea. So like x naught, you notice this is kind of parabolic in shape. Maybe it's not exactly a parabola. But if you start at x naught, it throws your root over here to x1. And then it starts going after this root. But you were looking for this one. So sometimes you have to be careful that it's going to not look for exactly what you're after. Take something with a lot of roots. This one you go, okay, well, I'm going to start closer to it. So you start close, but the problem is also, again, derivative's close to 0 here. So what happens is with that very shallow slope, it doesn't have the ability to throw this tangent line closer to the root that you're after. So it kind of just sends it over here. And now this function goes, oh, I'm over here. Oh, hey, I'm getting closer and closer to this root. And you're going, that's fine, that's fantastic, but that's not the root I need. So you have to be very careful with that as well. And so here's the homework. If you want to do it by hand, this little worksheet is basically just the spreadsheet that I would use. I highly recommend trying this in Excel. Learn it, do it by hand for a few steps, but if you're going to seriously calculate these, use Excel. You have technology. Use it to your advantage. Make it do all the grunt work that you don't have to do, or that you shouldn't need to do. But again, practice it by hand first, because you need to know what's going on with the process. You don't want to just say, shove it into a computer takes care of it, and then you haven't learned anything about what it's doing, why it's working, things like that.